Alright everybody, so today I'm going to talk to you about nuclear magnetic resonance. And this is a technique that actually uses a really powerful magnet, and it causes the spin of nuclei to all align and then randomly reverse their spin. And they get a signal from this. This allows them to tell what they call the environment of that particular nuclei. There's different types of nuclear magnetic resonance that you may see. The one that we're going to focus on is called hydrogen NMR. So the idea behind NMR, which you actually do not need to know for the exam, they don't ask you about it, but I thought that this might be helpful, is that normally the nuclei have a random orientation, a random spin to them. However, when we apply a really powerful magnet, we can get the spins to align. Now what's interesting about this is that there is a little bit of a difference depending on which nuclei it is, and they call this a precess, where you get this little bit of a wobble. Now what's interesting is that as we excite these nuclei, or align these nuclei through the magnet, they will send out a radio frequency pulse from the machine that will interact with the nuclei. And this radio frequency pulse that will interact with the nuclei will be absorbed by the nuclei. And what happens is every once in a while, the nuclei will then release a radio frequency pulse that is the same that they absorbed. And what this actually causes is a shift or a flip in their spin. And they show that here they are all aligned, north-south, and then over on this side over here, we see that there's been a flip from north-south to south-north. And the machine can record this. And depending on the environment of the hydrogen, where it is, how many carbons it's connected to, if it's connected to oxygen, that will affect the frequency of that outgoing flip. Now they call this resonance, and this is where the radio waves will have the exact frequency needed to make the nuclei flip over and spin in the opposite direction. So they get the right radio waves with the correct radio frequency in order to do this. So what ends up happening is you get the machine to graph this data. And the results that you see is the time it takes for the nuclei to flip over. And you can graph this and compare it to a standard. Now again, you don't have to know necessarily that much about how the actual machine works or what the flipping of the nuclei looks like, but at the same time though, you should have a general idea of what a shift is, which I'm going to talk to you now, and then how to read the graphs. That's really important. So the thing is that depending, like I said, what the hydrogen is connected to, what they call the chemical environment, will give off a different signal and a different shift. Now again, we're going to use hydrogen NMR, and there's hydrogen in all the organic molecules that we look at, and depending on where they are, they'll give information as to what atoms they're connected to and how many hydrogens are in that specific region. Now everything that they do is compared to a standard. The standard is called the TMS, it's tetramethylsilane, and here's my silicon connected to 4 methyl groups, and this will be what we always compare the other hydrogens to. So whenever you're looking at a graph for NMR, you will see that there is the standard TMS. So when we look at the TMS on a graph, here it is at the end here. And notice how there's only one peak for this, and that one peak shows that all of the hydrogens that are attached to the silicon and to the carbons in the methyl group are identical. Now if you look at this, this is a quite complicated NMR graph right here, because there's these triplets here, and even a quadruplet over here. We're not going to look at things that are that complicated. This again is just to give you an idea of the technique so that you can see what they look like, and give you an idea of what the graphs look like. So when we talk and look at a graph, we're going to look at the relative position of the NMR signal to the TMS standard. Now, you could do a mathematical shift for this, a delta, and figure it out mathematically, but again, we're not going to do that. So, let's look at what a graph looks like. So this is showing you the NMR from, a hydrogen NMR spectra for a molecule of ethanol. And so here's my carbon attached to 3 hydrogens, attached to another carbon, double bonded to an O and an H. And what we'll see is the following. We'll see that there will be a peak for the hydrogen that's attached to the carbon that's attached to the double bonded oxygen. And we'll get a peak, about here. We'll also get a peak along where we have the 3 carbons from the methyl group, 1, 2, and 3. And we'll get a peak up here. And then we'll also get a peak for our TMS standard at 0, because that's what we're comparing it to. Now what's interesting about this is we look at the height of the peaks, not only their placement. And so we see that this peak here is approximately 3 times the peak that we see over here. This allows us to tell not only the environment of the hydrogen, but how many hydrogens there are in that particular environment. Now, there is a standard table that you can look at and actually compare your results to. And so we can see here, for CH3, we're going to have a shift around 0.9 to 1. And that is not there. It should be over more at 0.9 to 1. So let's see if we can figure out, where is that shift coming from? Is there something around 2 here? And I guess I do see it here between 2 and 2.5 when there's a hydrogen attached to a carbon that's attached to a double bonded O. That causes those hydrogens, instead of showing up where the methyl group is, it causes them to show up at 2 parts per million, at a shift around 2 compared to a shift around 1. Let's see if we can find the aldehyde group, so the hydrogen attached directly to the carbon that has the oxygen there. See if we can find that, and looking for it. Oh, here it is. So you can see when I have a double bonded O and an H attached to this carbon, look at where the shift is. It came out right around 10. So you can use the table to get an idea of where the shift should be. You can use the height of the peaks to tell how many carbons there are. Notice this peak is 3 times as large as this peak, which is only 1, because there's 3 hydrogens compared to 1 hydrogen. Now we need to practice this. Again, we're going to look at simple diagrams like this. We're not going to get into the more complex ones. Now, just as an interesting aside before we stop, you can use NMR, or what people call MRI, magnetic resonance imaging. Everybody was freaked out when they used nuclear magnetic resonance. They thought there was some kind of radioactivity with it, which isn't true. And you can actually use this for body scans. And this is going to align the hydrogens in water molecules that are in a lot of your body. And you're able to use those, use that information to actually make a 3-dimensional view of organs and of different parts of the body. And they've really come a long way. They actually do something called functional NMR, where they can try the NMR when you have, in different circumstances. Maybe when you're, active versus not active, when you're reading versus not reading, and they can do this to tell if there's issues with normal function of your body. Alright, so here's an NMR machine. I don't know if any of you have had an MRI or an NMR done. It is really kind of a strange experience to have it done, but it is like a really incredible piece of machinery for diagnosing illness. Alright, so thank you for watching, and that is our instrumentation unit. We'll go over how to read the NMR graphs tomorrow, and thanks for watching.